Hello and welcome to today's tutorial. So today we're going to discuss on another application of an Opamp. So that is nothing but an integrator circuit. So now let us switch to our screen and we will see the basic definition of an integrator. So an integrator is a circuit which the output voltage is the proportional to the integral of the input voltage, or we can also see that an operational amplifier is a circuit that performs mathematical operation of integration, that is we can cause the output to respond to change in the input voltage over the time as the op-amp integrator produces an output voltage which is proportional to integral of the input voltage. So basically it is a circuit where we can produce a ramp kind of signals. So for example, the integrator are most widely used where if there is any square wave signals are there, and if you want to generate a sawtooth or a ramp kind of signal, so then the integrator circuits are used. Now if you look into the circuit of an integrator, it looks very similar to our inverting amplifier circuit. Only difference is that now instead of a feedback resistor, there is a feedback capacitor that has come into picture here. So now the same um, the voltage source is connected to an inverting terminal through resistor R1, and the output voltage is fed back to input through a feedback capacitor. Now we have to understand few properties of a capacitor here. So capacitor, initially when it is not charged, when it is having a zero charge, then it offers a very low resistance at that time what the capacitor starts charging. So as it starts charging and reach the maximum value, then at the same time it starts building its impedance, then it completely block the flow of DC when it reaches the maximum value, means the capacitor is fully charged. Now let us analyze this circuit, and then we will look into few examples of these integrator circuits, how this is used in forming the different waves. Now let us apply the KCL for this circuit. Now the current flowing to the inverting terminal here, V2, let me call this as IB. So if I apply the KCL to this circuit, then I'll get this equation as I1 is equal to IB plus IF. As we all know that the non-inverting terminal is grounded, so due to virtual ground concept, so V1 is approximately equal to V2, then our IB will become 0, approximately equal to 0. So then our equation is I1 is equal to IF. So now before applying the node voltage analysis, so let us write the mathematical equation for the capacitor current. So the mathematical equation of a capacitor current is defined as this C, that is the capacitance value differentiated the charge that it is holding, that is nothing but the voltage across the capacitor Vc. So now let us apply the node voltage analysis for this equation, that is I1 plus IF. So then that is I1 can be defined as the potential difference across the resistance R1, so that is given as Vs, so that is defined as the Vs minus V1 by R1, and this is equal to IF can be defined as again the potential difference across this. By using this second equation we will write, so that is given as Cf into d by dt of the difference of the voltage is given as V1 minus V0. So as we know that from this equation that V1 is approximately equal to V2, so this is nothing but 0. So now applying this, so this equation will become, it is just Vs by R1 equals, it is Cf of d by dt of minus V0. So if I rearrange this equation, so let me move this part here, let me move out this entire section to the right so that I have a space to so that I can create a space to write. So now I have to remove this differentiation part, so I'll integrate on both sides. So let us integrate from say 0 to t. So Vs by, what is that? It is R1. So equals integral 0 to t Cf d by dt of minus V naught. So now if we rearrange this equation and get the equation for V naught, so then we will get this as minus V naught is equal to minus 1 by R1 into Cf, because these are constants. Then integral of 0 to t, it is Vs into dt. So it is Vs into dt. So this is our equation for the integrator circuit to obtain the output. So now let us look into an example. So how this is, and before going to example, let me talk about this term, that is R1 into Cf. The charging time of the capacitor is decided by this capacitance R1. So higher the value of resistor, more the time it takes to reach the saturation level. So now let us take an example here. So let me clear this section, entire section. So here it is, circuit is given. So the same circuit is given like this, an integrator circuit. Need not to write the circuit every time, it is understood. The integrator circuit looks like this. Always it is having a resistor R1 and a feedback capacitor Cf, and this is R1 and this is V0. So this is V1 terminal and this is V2 terminal. Now question is that, so we have to determine the output for the given input, and it has to be considered that the capacitor initially, the voltage across the capacitor is 0, and the time constant, that is nothing but that is decided by R1 into Cf, which is equal to 1 second. So this is the time constant. So now the input waveform is given like this. So where the x-axis is the time in seconds, and the magnitude, that is Vs, that is the y-axis. So here it is defined that it is this. So this is magnitude is 3. So the time is from 0 to 5 seconds, its magnitude is 3. So that is what it means, the signal here. So now we have to see what is the output voltage. So let us take this equation here, V0. So V0 is equal to minus 1 by R1 into Cf integral of 0 to t into Vs into dt. So now we know that the R1 into Cf is equal to 1 second, so it is minus integral of 0 to t into now Vs value is 3 into dt, so we'll get this as minus 3t. So minus 3t, and so now if you look into this waveform, so now the value of t here, it ranged from 0 to 5 seconds. So how does the output waveform looks like from 0 to 5 seconds? So then if this is my time t here and this is the output voltage V0. So remember one more thing here, since the input source Vs is connected to a inverting terminal, therefore output is always a reverse case here. So we'll get an inverted output, that is why this symbol minus here. So it's very simple case. Now let us take the time t is equal to 0. So 0 into 3 is nothing but we will get it as 0. Now if the time is equal to 1 second, then we will get, so if the time is 1 second, then we will get a magnitude of minus 3. When the time is say 2 seconds, then we will get a magnitude of minus 6. Likewise, I do not have the space here, so let us create some space. I'll move this section here, then I'll move this section a little up here. Yes, so we have created enough space. Then likewise, if the time t is equal to 5 seconds, then what happens here? So here we have the points like this. So for t equal to 2 seconds, then we have a magnitude of minus 6 volts. Then for 5, we will get a magnitude of minus 15 volts, somewhere like this. So then we will get a line like this. It means we will get a ramp signal, negative ramp signal. So when the voltage is constantly positive at the input. So if this voltage changes, for example, if it comes like this to negative or it comes to 0, then what happens to this voltage is it will start decreasing because capacitors start discharging. So then we will get at another 5 seconds it will come back to 0. So next for another 5 seconds, then again it will come back to a maximum voltage of say minus 15 volts, and this pattern will continue to repeat if the input is continuously changing its form from +3 to 0 and 0 to +3, and accordingly the output voltage also creates a kind of a triangular wave, which is a ramp signal which is going from 0 to minus 15 and then minus 15 to 0 and so on, it continues. Okay, so now let us look into one more example here. So the another example is, it is given that the peak value is given as a 6 millivolts of 2 kilohertz is applied to an input of ideal Opamp integrator, where R1 is equal to 100 kilo ohms and CF is equal to 1 microamperes, 1 microfarad. It is not amperes. So if this is given, the peak value is given and frequency is given, then we know that it's a sinusoidal signal. It is given in the question itself. It's a sinusoidal signal. So the sinusoidal signal, its mathematical form of writing, a general form is AM into sine 2 pi ft. So that is 2 pi ft. So AM decides the magnitude of the signal. So F is the frequency of the signal. So if it is given, so it is a 6 milli into sine of 2 pi into, so here the F is say 2000 into T. So this is our Vs. Now if we integrate this with respect to the integrator equation, so then we have minus 1 by R1 into CF of integrating this 0 to T into 6 milli into sine. Milli you can keep it aside, so later we can write whatever the voltage, we'll get it as millivolts itself. So just write 6 here. So sine, so we have 4000 pi t into dt. So then we know that the integration of the sine is minus cos, so we will get a minus 60 of minus cos 4000 pi t by 4000 pi with limits 0 to t. Then finally we will get this as minus 0.015 by pi of cos. Now apply the limits 0 and t. So cos 0 we know it is 1, so therefore we will get this is cos 4000, we will get cos 4000 pi t minus 1 millivolts. So this is our final output. Now in exam, they may ask you to find the what is the output waveform that is generated by this integrator circuit. They will give some input waveforms. So let us see how to analyze this. So let me clear this section. So we have one more example here. So where it is given as R1 into CF is equal to 1 second. So this is given. So now the circuit is not important. We know that the integrator circuit, how does it look like? So I'll just write the waveform, the input waveform which is given in the question. So it is a square wave. So it is basically a square wave which oscillates between plus 2 volts and minus 2 volts for a duration of every 0.5 seconds. So you'll have a waveform like this, a square wave. So now this duration is 0.5 and here this is 1, and this is plus 2 volts and this is minus 2 volts peak signal. So now if this is our Vs, then what is our V0? How does our output waveform looks like? So now we have to understand our T. For the case, it is ranging from 0 to 0.5 seconds. Our Vs is equal to 2 volts, and for say 0.5 to 1 second, our Vs is equal to minus 2 volts. So now if we apply this to an integrator, then we know that it's the time constant is anyway it is 1, so it is integral of say 0 to 0.5. Let us write this as 0 to t itself, then it is 2 into dt. Then when we integrate this, we'll have a minus t here. So we'll have a minus t. So it means if you look into the waveform, so let me delete the unnecessary section here. So now that I'll shift this here, then the output waveform here V0 is given by, so now if we extend this, now this is 0, now till 0.5, what do we get? Now let us submit here the t is equal to 0. We'll have 0 when t is equal to 0.1. I'll get this as what do we get if I substitute 0.1? So let me clear this. So 2 into 0.1, I'll get it as 0.2. So likewise, if I keep on substitute, and if I substitute t is equal to 0.5, then I'll get it as 1. So, and since it is minus, so I'll get a negative peak of say minus 1. So I'll get a peak like this. So likewise for this case V0, so when we integrate, we'll get plus 2 volts. So sorry, it is a plus t we will get, because it is minus of minus, we will get plus t. So when you integrate, so now we have to keep on add this value for this, so then we will get the value. Now the capacitor has reached the maximum value, and since it's change in the polarity, so then the capacitor starts discharging. So for another 0.5 seconds, the magnitude will go back to 0, and this pattern will keep on repeating like this. So we will get a triangular wave with negative peak like this for this given input. Okay, so thank you for watching this tutorial. So in the next tutorial we will going to discuss on the differentiator circuit. Thank you.